Dear students, welcome to 21st online class of Control System Engineering. In last class we started root locus. If we have a closed loop system which have an unknown parameter and its transfer function depends on parameter, or in fact the characteristic equation defining poles of closed loop system depends on unknown parameter k, then we can't find closed loop pole location unless we know the value of parameter. So root locus gave us graphical representation of the path followed by closed loop system poles when an unknown parameter of the system is varied. Then we studied the vector representation of complex number, and after that formally defined root locus and the properties of root locus. If any point in S-plane is a part of root locus, then it must fulfill magnitude criteria and angle criteria. Now we will start today's lecture. Dear students, in this lecture you will study how to sketch a root locus and how to find the coordinates of the point on the root locus and their associated gains. Dear students, the contents of this lecture are rules for sketching the root locus, which includes number of branches, symmetry, real axis segments, starting and ending points of root locus, asymptotes, and j omega crossing. Dear student, we know that root locus is the representation of the path of closed loop system poles as gain is varied. For root locus, gain is greater or equal to 0, which means that for positive values of gain k, we will find out the path followed by closed loop system poles. From previous discussion, we know that a point in S-plane is a part of root locus, or the location of closed loop system poles for some value of gain k if it fulfills Engel's condition, which is that if we draw vectors from all the poles and zeros of the system to that point in S-plane, the net angle must be odd multiple of 180 degrees. Once sketch is obtained, it is possible to accurately plot just those points that are part of root locus. Following rules are used for plotting root locus for a closed loop system. Dear students, now we will start rules for sketching the root locus. The first rule is the number of branches of the root locus equals the number of closed loop poles. Now we know that if gain of the system is varied, each and every pole of the closed loop system will move. So we define a branch as a path that one pole traverse, then there will be one branch for each closed loop system pole. Second rule is the root locus is symmetrical about real axis. If we have complex closed loop system poles that do not exist in conjugate pairs, the resulting polynomial found by multiplying the factors containing the closed loop poles would have complex coefficient. So the root locus will be symmetrical about the real axis. Dear students, third rule is on real axis the root locus exists to the left of an odd number of real axes, finite open loop poles and or finite open loop system zeros. This rule is valid for poles or zeros of open loop system on real axis. Now consider the angle property of the point on the root locus to determine where the real axis segment of the root locus exists. If an attempt is made to calculate the angular contribution of the poles and zeros at each point P1, P2, P3 and P4 along the real axis, we observe the following. At each point, the angular contribution of a pair of open loop system complex 0 or pole is equal to 0. Secondly, the contribution of the open loop pole or open loop 0 to the left of respective point is 0. The conclusion is that the only contribution to the angle at any point comes from the open loop system real axis poles and zeros that exist to the right of the respective point. Dear students, now with the help of example, we will try to explain the third rule. As the rule says, on real axis, the root locus exists to the left of an odd number of real axis finite open loop system poles and or finite open loop system zeros. Now if you look at figure A, in this we have one open loop system finite pole and one open loop system finite zeros. And now if we start numbering the poles or zeros, then as per rule the root locus will exist to the left of pole at location -1 or to the right of 0 at location -2. Now if you look at figure B, in this we have 3 open loop system poles, and if we start numbering from right, we have poles at location -1, -2, -3, and these will be numbered as 1, 2 and 3. Now according to rule, root locus will exist to the left of odd number of poles. So one branch of root locus will exist between pole at -1 and -2, where second branch of root locus will exist to the left of pole at location -3. Students, now if you look at figure C, in this we have 2 open loop system poles and 2 open loop system zeros, and location and numbering are also mentioned here. Now according to rule 3, root locus will exist to the left of pole at -1 and to the left of 0 at -3, or we can say that to the right of pole at location -2 or to the right of 0 at location -4. So in this case we will have 2 branches of root locus, and in between the pole -2 and 0 -3 no root locus will exist. Now if you look at figure D, in this we have 3 open loop system poles and 2 open loop system zeros. The root locus will exist between the pole at -1 and -2. Another branch of root locus will be between 0 at -3 and 0 at -4. And last branch of root locus will exist to the left of pole at -5. These all branches specify that the region towards the closed loop system poles will move if gain of the closed loop system is. Dear students, Rule 3 defines region for root locus on real axis. Now the fourth rule is the root locus begins at the finite and infinite poles of open loop system G of S into H of S and ends at the finite and infinite zeros of open loop system G of S into H of S. Now this rule defined the starting and end points of the root locus, where previous point defined the region at which the root locus will exist on real axis. Now if you look at closed loop system given in the figure, its forward path system is represented by Kg of S, where feedback path system is represented by H of S. Now G of S is equal to Ng of S divided by Dg of S, and H of S equal Nh of S over Dh of S. Here N and D represents factor polynomials of numerator and denominator. Using this form, we can find closed loop transfer function T of S. Dear students, similarly we can obtain characteristic polynomial of closed loop system, which is 1 plus Kg of S into H of S equals zeros. Substituting the values of G of S and H of S, we obtain dg of S into dh of S plus k into ng of S into nh of S equal to 0. Now root locus give us path of closed loop system followed for varying the parameter k, and parameter k have values greater or equal to 0, which means that minimum value it can have of 0 and maximum of infinity ideally. Now if we substitute the value of k equal to 0 in the characteristic equation, we get dg of S into dh of S equal 0, which means that at start or for gain equal to 0, the closed loop system poles have location of open loop system zeros, which is kg of S into h of S. Now for maximum value of k, which is infinity, can also be written in the form of 1 over 0. Substituting the value 1 over 0 in the characteristic equation and solving the equation, we get ng of S into nh of S equal to 0, which means that at maximum gain or at gain equals to infinity, the location of closed loop system poles will be equal to the location of open system zeros. So we can simply say that a root locus will start from finite or infinite open loop system poles and will end on finite or infinite open loop system zeros. Dear students, now we will study about starting and ending of root locus with the help of example. If you look at the system in the figure A, in this we have two open loop system zeros and two open loop system poles. Two poles are located at -1 and -2, where zeros are located at -3 and -4. From last example, we concluded that when gain is equal to 0, location of closed loop system poles will be that of open loop system poles. And for gain equals infinity, the location of closed loop system poles will be equal to that of open loop system zeros. So that's why k equal to zeros and k equal to infinity are mentioned on poles and zeros respectively. Now from rule number 4, we know that root locus will start from open loop system poles at -1 and -2, and this root locus will end on zeros at -3 and -4, as shown in the figure B. From rule number 3, we know that on real axis, root locus will exist between the poles at -1 and -2, and also between the zeros at -3 and -4. So when gain is varied, the poles of closed loop system will move towards the region where root locus exists. On the real axis, they meet somewhere between the two poles and break out into the complex plane, moving as complex conjugates. Now these poles return to the somewhere between the zeros at -3 and -4 and reaches their final location, which is location of zeros of open loop system, that is -3 and -4, and their path is completed and ended up respectively. Dear students, in rule number 4 we studied that root locus will begin at finite or infinite poles of g of s into h of s and will end on finite or infinite zeros of g of s into h of s. Now our next rule is rule number 5, which says that the root locus approaches straight line as asymptotes as the locus approaches the infinity. Students, this rule defines the path through which the poles approaches the infinity, or if zeros of the open loop system lies at infinity, then asymptotes will define their path how they will approach the infinity. For these asymptotes, 3 basic quantities are required. First is number of asymptotes, which is equal to n minus m. Here n is finite number of poles and m is finite number of zeros. Second thing is center of asymptote on real axis, or the point on real axis from where asymptotes will start. This will be equal to sum of finite poles minus sum of finite zeros divided by number of asymptotes, or finite number of poles minus finite number of zeros. Last quantity for asymptotes is angle of asymptote, through what angle they will originate on real axis, and this is equal to odd multiple of pi or odd multiple of 180 degrees divided by number of asymptotes. And here k is equal to 0, plus minus 1, plus minus 1, plus minus 2, and so on. And the angle is given in radians with respect to positive extension of real axis, or angle can be used in degrees form. Then we Dear students, now we will sketch the root locus for a closed loop system given in the figure. The forward path of the closed loop system is given by g of s, which is equal to k into s plus 3 divided by s into s plus 1, s plus 2 and s plus 4, which means that if we found open loop transfer function, in this case will be kg of s will have one finite zero and 4 finite poles. For root locus of the closed loop system, first of all we will draw pole zero map of open loop system, and then we will apply rules used in sketching of root locus, which include number of branches, symmetry, real axis segment and starting and ending points. Now for real axis, we know that root locus exists to the left of odd number of poles and zeros. So root locus here will exist between pole at origin and -1, pole at -2 and a 0 at -3, and onwards or to the left of pole at -4. These segments define the region where pole will move when gain k is varied. Now we know that as gain is varied, root locus will start from poles of open loop system and will end on zeros of open loop system. In this case, we know that we have 4 finite poles and 1 finite zero, which means that we have 3 zeros of open loop system at infinity. Now 3 branches of root locus will end on infinity and their path will be defined by asymptotes. Dear students, in this example we know that 3 branches of root locus will end on zeros of open loop system which lies at infinity, and for this we will find asymptotes. The number of asymptotes will be equal to number of finite poles minus number of finite zeros, which equals 3. Now the center of asymptote will be sum of finite poles minus sum of finite zero divided by number of asymptotes, and this is equal to -4/3. This will be the center of asymptotes at real axis. Now the angle of asymptotes on real axis will be equal to odd multiple of pi divided by n minus m, or odd multiples of 180 degree divided by number of asymptotes. If k is equal to 0, angle of asymptote will be pi divided by 3 radians or 60 degrees. For k equals to 1, angle of asymptote will be 180 degrees or pi radians. And for k equals to 2, angle of asymptotes equal 5 pi over 3 radians or 300 degrees. Now if you look at figure A, we have drawn 3 asymptotes with the angle of +60, 180 degrees and 300 degrees or -60 degree, where center of asymptote is -4/3. Now in last slide we have defined the root locus segments on real axis. Now we will draw asymptotes on pole 0 map. One asymptote will have angle of plus 60, second will have 180 degrees, and last will have angle of 300 degrees or minus 60 degree. Now when gain is varied, the poles will move along the root locus segment defined in last slide. Now pole at minus 2 will move toward 0 at minus 3. Pole at minus 4 will move toward a 0 at infinity along the real axis with the angle of 180 degrees. As gain will be varied, the pole at origin and second pole at minus 1 will move towards the root locus segment, and at some point they will break away from the real axis with the angle of 90 degrees, and then they will follow the path defined by asymptotes and will reach to zeros at infinity. We can also analyze that for certain values of gain k, poles of closed loop system will enter the right half plane, and for those values of gain k, our closed loop system will be unstable. Dear students, next rule in the sketching of root locus is j omega crossing. The j omega crossing is a point on the root locus that separates left half plane from right half plane, or we can say that separates the stable operation of the system from unstable operation. If closed loop system poles lie on imaginary axis, then its response is oscillatory, and the value of omega at the j omega axis gives the frequency of oscillation. Now to find j omega crossing, we use the Routh-Hurwitz criteria, and forcing a row of 0 in the route table will give us the value of gain, and going back one row to the even polynomial equation and solving for the roots, we get frequency of oscillation at imaginary axis. Dear students, now we will continue the last example for the value of gain k and frequency of oscillation at imaginary axis, and we will also find for what range of gain k the system is stable. Now for solution, first of all we will find closed loop system transfer function, which is given by t of s, and the characteristic polynomial for the closed loop system is the denominator of the closed loop transfer function, which is given here. Now we will construct a route table with the highest power of the characteristic polynomial, which is equal to 4. Dear students, now we will construct a route table with the highest power of characteristic polynomial, which is 4. Now we will label each row as S4, then S3, S2, S1 and S0. We will place the coefficient of characteristic equation in first row labeled as S4, and will skip every next coefficient, and all the skipped coefficient will be placed in the second row labeled as S3. For further rows, we will use the rules of route table to complete it. Students, here we are finding the value of gain k, for which we will have poles of a system on imaginary axis, and we have to find value of frequency. Now poles will lie on imaginary axis if we have a complete row of 0. And for positive values of gain k, for which root locus will be plotted, only S1 row can give us a row of zeros. Thus, minus k square minus 65 plus 720 equals 0. From this equation, the value of gain k equals 9.65. For this value of 9.65, we will form even polynomial at row labeled s square. And the even polynomial will be 90 minus k s square plus 21k equals 0, or 80.35 s square plus 202.7 equals 0. Solving for the value of s is found to be equal plus minus j 1.59, which will be the frequency of oscillation. So we conclude that the root locus crosses the j omega axis at plus minus j 1.95 at a gain of 9.65. Also, our closed loop system will be stable for range of k greater than 0 and less than. Now if any of you have any questions, please ask.